When you exercise, your muscles aren't just getting stronger, they're setting off a biochemical storm. You might think lifting weights or running builds muscle directly, but it's actually microscopic damage that triggers growth. Tiny tears in muscle fibers send a distress signal, prompting your body to repair and fortify these fibers. This process is controlled by satellite cells, a type of stem cell residing around your muscles. Once activated, they multiply and fuse with existing muscle fibers, adding new material. This not only repairs damage but also allows muscles to grow larger over time. A single workout can activate these cells in under 24 hours. Why does your heart race when you exercise? It's not just about pumping more blood, it's about prioritizing oxygen delivery. Your body diverts blood from less critical areas like digestion to muscles and skin. This ensures muscles receive oxygen and nutrients while skin dissipates heat. During intense exercise, your heart can beat up to 200 times per minute, a rate governed by the autonomic nervous system. Adrenaline floods your bloodstream, enhancing this response. This automatic system adapts on the fly, optimizing your body's mechanics for survival and performance. Despite the increased demand, your heart becomes more efficient with regular exercise. Inside your muscles, energy production transforms dramatically when you exercise. At rest, your muscles primarily burn fat for energy, but as you start moving, your cells switch gears, relying on stored carbohydrates called glycogen. Glycogen breakdown provides a quick energy source necessary for bursts of activity. This transition is orchestrated by enzymes that respond to rising energy demand. Within seconds, your muscle cells can increase energy production up to 20 times the resting level. This swift adaptation is vital for endurance and strength, highlighting the muscle's role as a dynamic power plant. Lactate, often misunderstood as the cause of muscle soreness, actually serves an essential role. During intense exercise, when oxygen levels dip, your muscles switch to anaerobic energy production. This process generates lactate, a molecule that can be used as fuel by your heart and other muscles. Far from being waste, lactate helps delay fatigue and maintain performance. Your body can clear lactate in as little as 30 minutes post-exercise thanks to specialized transporters. This rapid turnover indicates how effectively your body recycles energy substrates, preparing you for the next challenge. Muscle pain post-exercise isn't lactic acid but rather microscopic tears from exertion. This soreness, known as delayed onset muscle soreness (DOMS), peaks 24 to 72 hours after activity. It occurs as your immune system deploys cells to repair damaged fibers. These cells release signals that increase blood flow and initiate repair processes. This is why you feel tenderness and stiffness. Your body is working hard to make muscles more resilient. Surprisingly, this cycle of damage and repair strengthens muscles, illustrating the body's remarkable capacity to adapt and improve. Delve into the microscopic world of your muscle cells where mitochondria reign as powerhouses. These tiny structures convert nutrients into adenosine triphosphate, ATP, the energy currency of your cells. During exercise, your muscle fibers demand a rapid surge of ATP. Mitochondria respond by upregulating oxidative phosphorylation, a process generating ATP through electron transfer. Astonishingly, each muscle cell contains hundreds to thousands of mitochondria, each working like a mini power plant. With regular exercise, the number and efficiency of mitochondria increase, enhancing your stamina and performance. This cellular adaptation underscores how your body optimizes energy supply. Dive deeper into molecular chemistry with creatine phosphate, your muscles' backup energy reserve. When ATP depletes during intense exercise, your cells tap into creatine phosphate. This molecule rapidly donates phosphate to regenerate ATP, fueling short bursts of activity. This phosphagon system is crucial during high-intensity efforts like sprinting or lifting weights. Within seconds, creatine phosphate can double your available ATP. However, these stores are limited, lasting only about 10 seconds of maximal exertion. The speed and efficiency of this system highlight your body's preparedness for sudden demands. Calcium ions play a pivotal role inside your muscles, acting as messengers for contraction. When a nerve impulse reaches your muscle, it triggers the release of calcium from the sarcoplasmic reticulum, a specialized storage within cells. Calcium binds to troponin, a protein on the actin filament, shifting its position and allowing myosin heads to attach. This interaction initiates the sliding filament model of muscle contraction, where actin and myosin filaments slide past each other. This mechanism is crucial for every voluntary movement, from lifting weights to tapping your foot. After contraction, calcium is pumped back, resetting the muscle for the next impulse. Your nervous system orchestrates muscle contractions with precision, using motor units. A motor unit consists of a motor neuron and the muscle fibers it innervates. When you decide to move, your brain sends an electrical signal down spinal neurons to these motor units. The size of the motor unit determines muscle control, small units for fine movements, larger ones for powerful actions. During exercise, your body recruits more motor units for greater force. This recruitment can be measured as an electrical activity known as electromyography, EMG. The diversity and adaptability of motor units illustrate the intricate control your nervous system has over movement. Hormones are unsung heroes in muscle adaptation. When you exercise, the pituitary gland releases growth hormone, which stimulates muscle repair and growth. Simultaneously, cortisol, a stress hormone, helps mobilize energy reserves by breaking down fat and protein. Insulin-like growth factor 1, IGF-1, produced in response to growth hormone, enhances protein synthesis. The interplay of these hormones orchestrates a balance between energy availability and muscle building. Interestingly, testosterone, prevalent in both men and women, also promotes muscle growth through protein synthesis. This hormonal synergy is crucial for adapting to the physical demands placed on your body. When muscles reach their limits, fascinating mechanisms kick in. Consider muscle fatigue not just a sign of tiredness but a complex interplay of factors. Fatigue results from a depletion of energy reserves, accumulation of metabolic byproducts, and altered neural input. During prolonged exertion, ion imbalances, especially of potassium and calcium, disrupt electrical signals. This reduces muscle contractility, a protective measure against damage. Intriguingly, fatigue begins as a defense mechanism, ensuring muscles don't push beyond their sustainable threshold. The body's ability to limit exertion reveals an inherent wisdom in preserving cellular integrity over short-term performance. Muscles can adapt to extreme conditions, growing stronger under stress. Take hypertrophy, triggered by consistent high-intensity workouts. This growth results from mechanical tension, muscle damage, and metabolic stress. When your muscles experience these conditions, they activate signaling pathways, notably the mTOR pathway, critical for protein synthesis. This pathway regulates cell growth and proliferation, underpinning muscle mass increase. With continued stress, muscles enhance their architecture, increasing in size and strength. Your body's ability to adapt to such extremes demonstrates its incredible capacity for growth and transformation under pressure. Rarely, the muscle system can fail catastrophically, revealing its limits. Rhabdomyolysis is a condition where extreme muscle breakdown releases myoglobin into the bloodstream. This can occur from overexertion, crushing injuries, or even certain medications. Myoglobin can overwhelm the kidneys, leading to potential failure. This condition underscores the importance of balance, as even your adaptable muscles have boundaries. Despite this, your body generally manages damage well, with mechanisms in place to repair and recover. Such failures remind us of the fine line between pushing limits and respecting the body's natural thresholds. At the cellular level, oxygen deprivation unveils another extreme. Hypoxia, a condition of low oxygen, can occur during intense exercise. When oxygen is scarce, your muscles partially switch from aerobic respiration to anaerobic pathways. This triggers hypoxia-inducible factors, HIFs, which adapt cells to low oxygen by promoting angiogenesis, the formation of new blood vessels. This adaptation increases oxygen delivery, enhancing endurance. Your muscles' ability to trigger angiogenesis shows their capacity to adapt structurally under sustained pressure. Such cellular resilience is vital for survival and performance in low-oxygen environments. The most surprising truth about your muscles lies in their versatility. Muscles are not just for movement but also act as endocrine organs. When you exercise, they release signaling molecules called myokines. These molecules communicate with various systems, including the immune system, influencing everything from fat burning to brain function. Myokines like interleukin-6 play roles in inflammation and metabolism. This hormonal activity highlights how interconnected your body's systems truly are. Your muscles are more than mere engines of motion, they're dynamic communicators shaping your entire physiological landscape.